today's discussion is going to be around the other major skills. We said yesterday that if you think about data science, the three core skills that you require there. One of them is programming. The other is maths. So there's a certain bit of mathematical rigor that is involved with becoming a data scientist. So there's a certain amount of maths or mathematical skills that are also required. Then you got business intelligence. Now, yesterday we tried to give you a flavor of this. We tried to give you a flavor of programming. We also, in the initial bit, we also talked for about 15-20 minutes around some of the common applications for data science across different sectors, different parts of businesses, across different industries and functional roles. That was something that was intended to give you some flavor for business intelligence as well, to give you a sense of how this space is getting applied across different areas. Today's discussion will focus on the maths part of the conversation. What we'll try and do is we'll at least try and get a sense of two ideas in mathematics. We'll try and see how these ideas are useful. One of them is statistics. The other is probability. We'll see how these two mathematical ideas correlate to data science as a space, how these areas could actually help us explore some of the major ideas in data science. So that's the purpose, that's the primary aim of today's discussion. We'll try and talk about some of the ideas in statistics. We first try and understand what these two branches of maths are all about. Now, for anybody who's coming from a proper engineering background, would probably have gotten exposure to these skills during high school level. A lot of folks, even from non-technical backgrounds, also do have exposure to these topics, at least in the form of ideas. Therefore, these are not topics that are too out of the way for us. So we'll try and understand how statistics as an area in mathematics, similarly probability as an area in mathematics, how these two topics actually help us work with data science problems. We've sort of gotten a sense of what typical data science problems look like. And this discussion will also give us some more understanding in that direction to get a sense of how these ideas move around in the data science space. So we'll start off with statistics. Now, statistics, to very crisply put it, it's a science of measurement. To put it in the simplest way possible, statistics very simply gives us some of the very basic ideas to help us start measuring things. Now, in order to study any event, in order to study any process, one of the first things that you've got to start doing about it is start understanding it in a quantifiable way. When I say a quantifiable way, the reason why we were able to make nuclear reactions sustainable, we were able to power nuclear reactors was because we were able to go through it. The processes that are involved in fission or fusion, you were able to measure certain parameters around that activity. When you started measuring those parameters around that activity, that is when you felt that, okay, there are certain benchmarks to be created so as to keep in mind that certain levels do not pass, or else there could be a critical scenario. Now, that is with nuclear science. That is the same thing is true with any science. In order to advance in a particular area, one of the first things that you got to start doing is to start understanding certain processes in a quantifiable way. What is it about a Netflix product? What is it about Netflix that you can measure so as to understand whether the company is going in the right direction or the wrong direction? Statistics is one of those sciences which is going to help you start quantifying the product in defined ways. And then the moment you are able to start quantifying it, you'd be able to start working on how to improve the characteristics of any observation, anything that you're trying to deal with in terms of those features, in terms of those distinctions. So statistics is a science that helps you with measurement. So we start off with a quick discussion around statistics. We'll try and talk about what are some of the major areas in statistics that help you understand data science problems, deal with data science problems. But that discussion starts off with analysis itself. So we're going to start off discussing about analysis. So there are three kinds of, majorly there are three broad categories in which you could divide any kind of analysis that happens in the industry in the space of data science. The first kind is descriptive. The first kind of analysis that you encounter is descriptive. The second is predictive. And then you've got prescriptive. Right? To understand exactly how these three kinds of analysis are different, what I'll need to do is, we'll try and make this an engaging discussion. So I'll try and ask you to put in some of your feedback, and I'll look through it in the comments, and we'll try and see if we are able to think in the same direction, and we are able to get to an objective or not. So what I'll try is, we'll think of a case. We'll take a simple case. The case is, let's say I'm Tata Motors. Now, the top management in Tata Motors has hired some of us into a role wherein we've got to look at the product. We've got to look at one product, and that is Nexon EV, the electric variant of Tata Nexon. So this is the product that we've got to work on. Our role is to identify areas. So the first version of the vehicle is already out in the market. It's already selling, let's say, for a period of 2 years. The first version of the vehicle is already out in the market and selling for the last 2 years. Tata is now developing a prototype for the second version, and it's hired analysts from different spaces to basically do proper research and make sure that the launch of the second version tries and improves upon some of the major problems that people faced with the first version, and it is planned in such a way that the whole sale and everything goes very well. So the whole merchandise sells well. It becomes, say, one of the best-selling products of the company. That's the aim for the team, and you're trying to figure out as a person, as an analyst, you've got to create a map for what we should do in the future, or how is it that you're going to analyze this problem. Your role is to own this product and make sure the second version that comes out is going to do much better than what the first version did. And let's say the first version also did decently well. Now, in that case, what I need you guys to do is, I want you to send me inputs on what are the things that you would start off with. What are the things that you would like to know about the product that would help you function inside this role? Imagine yourself in this role, that you're the owner of the product. How do you've got last 2 years of history for the first version. What are the things that you start looking at? I want to look at your point of view. So start putting it in the comments. I'll look through those and we'll keep discussing as we go on. I hope you understood the scenario. The scenario is simple. You've been assigned a role of trying to work in a product environment. You've been given ownership of a product that is Nexon electric vehicle, the EV version of it. The first generation of the vehicle is already out. It's been selling for the last 2 years. A team has been created to basically look at how that happened, how the whole sales is going, and then create a path so that the second version, which is, say, going to be launched in the next 6 months, how do we create the right path such that that launch is a success? So that's the goal. What are the things that you start looking at as an analyst? If I were to ask you this question, you've probably got no knowledge of what data analysis is like, but common sense, if you were to think of questions in your mind, what would you look at? Okay, we start getting okay. So people are saying model. So you're looking at parameters, right? So you're saying model, safety, mileage, design. You've also got to keep in mind that you've got to think about aspects that an analyst can improve on, not about aspects that would require a design engineer to bring about a change. So if there's a change in the design, that is something that the design engineer will have to do. You could bring in feedback. So yeah, Customer feedback is something that is quite crucial. Customer feedback. All right. What else? Customer satisfaction, people say. Yeah, so you could look things like NPS scores. NPS score is a net promoter score, a score that you get in the range of 0 to 10. The higher the value, the better it is. The greater the likelihood that the person is completely satisfied with your service. So there are different ways of tabulating it. As a data analyst, as a person who looks at data, some of the other things, okay, so somebody says competition in the field. That's interesting as well. So you'd like to analyze your competition as well. But let's first start analyzing ourselves. See, the starting point of this analysis is to understand what the status quo is. What's the current situation? You need to understand what or how the first generation model sold in the last 2 years. So you first start looking at historical sales data. The first thing that you might be interested in looking at is to first understand what is the level, what is the average level at which the previous version of the product was originally selling. Only once I'm able to establish that baseline, will I be able to set or understand for myself what is going to happen over the next 2 quarters, or 3 quarters, or 4 quarters, or 6 quarters, if that is something that I want to do. But unless I start looking at what has happened in the last 2 years, there's no way of at least starting this analysis. So this analysis starts off by looking at historical data. Now that data has to be looked at in several views. So you need to understand by salesperson, by region, by city. So you understand how sales have been across, say, the last 24 months, across different cities, across different regions. You first collect that data. That's the first part of analysis. That's the first step of analysis. You understand that analysis. If you think about what you're doing at this point, you're basically trying to undertake the first step. The first step of analysis, which is descriptive analysis. Now, descriptive analysis or descriptive statistics, to be specific. So descriptive statistics is one way of doing descriptive analysis. Is something that allows you to look at historical information and analyze what happened, how it happened, where it happened. So answer the basic questions of what has happened on a certain amount of data. So you look at a certain amount of data. Here in this case, it could be the last 2 years of sales across different regions, geographies, demography. So across different parameters, you try and understand how sales have moved to get a sense of what the company has been doing or what the product has been doing in the last 2 years. So that analysis, when you look at a certain amount of data and try and understand what are things that have happened there, that kind of analysis is called descriptive analysis. That's the first basic analysis that you start off with. The second step is to start hedging for the future. You look at as a person who is owning the second generation, you've got to be able to create algorithms. You've got to be able to create processes such that you can estimate what you are estimating to sell in the first 3 months or the first 6 months or the first year of its launch. So when you're trying to bring in a new line, how do you estimate how much you've got to produce? How much do you put in inventory? How much do you put across different cities in the country? So you've got several questions to answer. To answer those questions, you've got to think along the lines of, if I'm in June 2021, if my product is going to get launched in June 2021, I've got to have a clear map of what I can expect in the next 3 months, 6 and 12 probably. I need to have a clear picture of what is it going to take over the next 1 year for me to manage this product. This kind of analysis, wherein we look at historical information and we try and predict things into the future. We try and expect what you can expect to see in a business. These kinds of analysis are typically called predictive analysis. When you try and look at a certain amount of information, based on that information, you try and interpret, or you try and analyze, infer what's the expectation, say, in the future, or in cases where you don't know. Now, this is an analysis which we are talking about in terms of time series data. So this is time series data. The reason why I call it time series data is because time is a factor here. You're looking at sales in the last 12 months. So you're trying to understand that in a graded way. Now there are different kinds of data sets. Let's say the problem that you're facing is that you are a healthcare company, and you've just realized that there are certain kinds of diseases that you can predict based on looking at MRI scans, and you build a model to look at MRI scans. So the way that model gets created is that you bring in MRI scans for say 100,000 people. You know exactly for them whether they had the disease, so yes, or they did not have the disease. You know across this 100,000 people whether they had the disease or did not have the disease. You look at all of their MRI scans, and you allow the model to learn whether, by looking at a certain MRI scan, if you can predict whether a person has a certain disease or not. Now, when a new person comes in, when you do this analysis, when you try and understand what happened with these 100,000 people, the next natural step is to be able to create something that can look at any new person that comes in, upon which the model has not been trained. It can look at any new data and still be able to predict whether he has a certain disease or he does not have. He does not have that disease. This would also be predictive analysis, because you're basically trying to look at a certain amount of information, understanding how the inherent process is working, how that data has behaved in that size that you've looked at. And based on that, you're trying to take a call on what could happen in the next set of new data points that you look at. So that kind of analysis would be called predictive analysis. The third kind of analysis that you come across typically is prescriptive analysis. Now, this helps you answer a slightly more advanced kind of question. To give you a sense of what that question could be, let's take a simple case in marketing analytics. We look at a simple case in marketing analytics where there's a company that is selling TVs. It sells its TVs, but it runs a lot of ads as well to do that. The ads that it runs are running on TV, radio, newspapers, social media platforms, and billboards. Let's say the company is selling TVs, and it is doing ads for its product across these 5 channels. Now, a typical marketing analytics project that exists in the space is wherein analysts try and figure out. So let's say in the month of March, the company sold 2,000 units of TV. If the company sold 2,000 units of TV across the 5 marketing channels that you had TV, you had digital, you had radio, you had newspaper, and you had billboards. Across these 5 channels, what are the relative spread of this number 2,000 across these 5 channels? This kind of modeling is something that is very useful for marketers. If you're able to analyze that across my 5 or 6 or 10 channels that I'm doing marketing, which channels are contributing more to my sales, that leads me to the automatic next step where I'm able to decide that if I get an additional $1,000 in marketing, where do I spend it? Let's say I've realized that out of the 2,000, I get most of my sales, about 1,500 of them TV, and the rest 500, they get distributed between these 4 channels. Now, if I get an additional $1,000 and I've got to spend that $1,000 in some space to try and improve upon how we are selling, in that case, those $1,000 go into which channel? If you were the marketer, based on this information that you just looked at, if you got another $1,000 to spend, on what channel would you spend the $1,000? Can you decide that channel here? You've got 5 channels. in the month of March, you just realized that out of the 2,000 units that you sold, 1,500 of those units came from marketing that happened in the TV channel. The rest of the 500 units came from marketing that happened across digital, radio, newspaper, and billboards. Now, if you get another $1,000 as a marketer, in which channel do you spend those $1,000? Do you spend it on any one channel, or do you spend it across multiple channels? Exactly. So a smart marketer having these additional $1,000, he realized that it's optimal to only spend it on TV, because he realizes that most of his sales, most of his product, a large percentage of the product is only being sold on the TV channel. Which is why this kind of a question goes into the realm of prescriptive analytics. See, this is a very popular project. It's called market mix modeling, a very popular data science project. It is done, it's useful for companies across a lot of industries. Almost every industry is doing marketing of some kind. And it's not just 5 channels. Mostly companies are spending across 10, 15, 20 channels, at least the larger companies. And they consistently find value in analyzing what percentage of their channels are really effective. So it's not simply about absolute sales. It's also about the idea of ROI. So you're also interested in ROI. ROI is simply return on investment. So if you're spending a certain amount of money in a certain segment, how much return are you getting out of it? So return on investment. Now, this kind of analysis, wherein it's no longer about simple predictions. A simple predictive analysis would try and build a model which is able to predict something like this. Y is a function of, say, 3 variables. What are these 3 variables? Y is your sales. You're saying that the total sales of TV is something that depends. Function indicates that if you give me the values of x1, x2, and x3, I'll be able to give you a value for y. What are x1, x2, x3? Let's say this is marketing spend in the channel TV. This is the marketing spend in the channel radio. This is the marketing spend in the channel newspaper. Now, you ultimately try and create models around these. You try and create a model that helps you look at your spends across these 3 channels and analyze what the relevant level of Y would be. So if somebody tells me that, okay, I'm going to spend $500 on TV, 300 on radio, and 200 on newspaper. Predictive analysis means using a functional relationship like this to basically get the input values, and based on that be able to say that the expected value of Y is 1,500 units. Predictive analysis helps you do this. When it comes to prescriptive analysis, that is slightly different. It is not trying to answer predictive kind of questions that if I give you the input variables, what is the value of Y? It is trying to answer questions like, out of the 3 channels that you spent money on, which of the channels was more helpful? When you try and answer questions like that, it's no longer just about being able to predict, just about being able to take in a set of input values and being able to predict what the Y is going to be. It's also about understanding which of those inputs are actually contributing more as compared to the inputs that aren't contributing as much. Now, when you go to that kind of an analysis where you realize that TV is the most effective channel, that is when the analysis becomes really good from a prescriptive point of view, and that changes the nature of the analysis from predictive to prescriptive. So the simple idea of the whole discussion is that when you look at a certain amount of data and you just try and understand what happened across that data set, whether it was you looked at 100,000 MRIs of people and you understood how is it that you can identify whether a person has a disease or not, or you looked at last 12 months data, last 12 months information for sales of a particular entity and tried to analyze what happened in those last 12 months. When you're answering questions by looking at the data and then trying to analyze only for the data that you're looking at, that is when the analysis is descriptive. When you move on and start predicting, you start predicting generalized inferences, that is when the analysis becomes predictive in nature. In the process of doing predictive analysis, we also encounter prescriptive analysis. Now, how does statistics help you in that space? Statistics offers some ways of dealing with certain kinds of problems. It gives you a descriptive statistics way of thinking, and it also gives you a inferential statistics. So these are two schools of thought. In fact, these are basically two ways of solving two different kinds of problems. See, descriptive statistics is simply trying to look at a certain amount of data. Let's say I go to a school, analyze all the sixth graders in that school, and try and understand what's the relative proficiency of math students in that school. That kind of an analysis is called descriptive analysis. You went to a school, looked at 60 people, tried to analyze what's the situation in those 60 people. If I tried to make an inference for the general crowd of sixth graders in the state of Karnataka by just looking at the sixth graders of one school, that is when that the analysis can no longer be called descriptive, because you're looking at a certain amount of data, but you're trying to draw inferences about a much larger crowd. If you're doing something like that, that is when you need the help of inferential statistics. Does that make it clearer? I hope it does. Super. So the idea here is to try and understand how these two schools of thought inside statistics are different. Now, the reason why they're different very simply is because there's a need for it. There are two kinds of problems that you typically come across. Your problems can be of two kinds. Depending on the nature of the problem, you decide whether you look at it from a descriptive point of view or you look at it from an inferential point of view. Now, descriptive statistics, what it does is, let's say you've collected data for 100 10th graders, and you've looked at the marks that they scored in mathematics. If you look at these 100 10th graders and you see that the average marks that they got is 80, these are 100 10th graders from a particular school in Karnataka. Let's say you've looked at a particular school in Karnataka, and your purpose is to analyze how students in that school is doing. You are the headmaster of that school, and your purpose is to analyze how the students in that school are doing with respect to mathematics. And you looked at their average scores. You realize that the average scores are 80. If you look at this average and you try and understand or you try and analyze only what has happened with those 100 10th graders that you looked at, that kind of an analysis is called descriptive analysis. So descriptive analysis, if you're trying to do descriptive, if you're trying to analyze something in a descriptive way, you need to have the data for the observations that you're looking at. If you want to analyze these 100 10th graders, you need to have data for all the 100 10th graders. You look at their scores across mathematics, across the 100 students, you take an average. One of the common measures or one of the common ways in which descriptive statistics get used is by using measures of central tendency. We'll talk about that in a little detail as well. We'll talk about what central tendency is and how central tendency can help you describe or understand data well. Now, in this case, you're looking at 100 10th graders and you've tried to analyze only those 100 people, and therefore the analysis is descriptive. But you look at this data and you try and infer something. If you try and make a conclusion about all 8th graders in Karnataka or all 8th graders in that particular city, then that is something that goes into the realm of inferential statistics. Inferential statistics gives you ways in which you can deal with that. See, descriptive statistics requires you to have the full data for whatever you're trying to analyze. But there are some problems that you just cannot approach in that way. To give you an example, think of exit polls. Imagine you're a company that has to do exit polls. Imagine yourself in that position. You've got to do exit polls, and let's say it's just been decided that there have been elections in the state of Bengal recently. Let's say elections have just happened, and you want to do an exit poll. The purpose of the exit poll is to be able to figure out the preferences of all the people in Bengal. if you try to take a descriptive approach to running the exit polls, what that would require you to do is, it would require you to go to every household in Bengal, figure out what their preferences are, tabulate that information, and then on that take a decision on what the exit polls should be indicating. Now, if you're able to do that, then we wouldn't need an election commission, right? If simple agencies could go out to the entire state and figure out the preferences of the entire state, why do elections and why get into all of this machinery to put so much effort into it? Which means that that is a task that is simply not possible. The size of the population is so huge. If you're trying to understand the preferences of people in Bengal, they're close to 3 crore people in Bengal, which means that trying to understand that their preferences by tabulating data for the entire 3 crore is definitely not a feasible solution. If the government of India also has to decide how many schools to build in the state of Bengal, or the government of West Bengal has to decide that, it's not really possible to go out to every person in Bengal and ask what their preference is. What they've got to do is, they've got to be able to, if they've got to reach out to a population as large as that, they need to have some way in which they don't have to reach out to that entire population, and still they're able to figure out what the population wants. And that is what inferential statistics does for us. What inferential statistics allows you to do is, let's say you've got a very large population. The population in this case is the whole, so 3 crore people in Bengal. So the entire crowd of population, the entire crowd of people in Bengal is the population in this case. You're trying to understand the preferences of this entire population. What inferential statistics does is that it gives you some really efficient ways of basically drawing a sample out of this population. Now this we call the population, the smaller group we call a sample. The sample is a very small fraction of the population. Now, what inferential statistics allows you to do is, instead of collecting data for the entire population, it says that you don't need to do that. You can just collect data for a smaller sample and use that to basically infer what the entire population wants. Inferential statistics will give you a way to generate data for a smaller sample. If you had to generate data for population, if it were possible, you could just have gone ahead and looked at the entire data and decided what the preferences were. You would have needed descriptive statistics tools, but not inferential statistics. But because this population is so huge, trying to understand their preferences surely it cannot mean that we'd have to go out to everybody and ask what their preference is. What inferential statistics allows us to do is, it allows us to create a much smaller data set. When I say create a data set, it basically means that we'll have to look at a smaller segment. So if the 3 crore people there, maybe we go out and survey 30,000 people. We survey 30,000 people in Bengal, but we do that intelligently in such a way that when we analyze that 30,000, because we've only collected data for 30,000, our analysis is built on those 30,000 people. But inferential statistics gives you ways to ensure that whatever analysis you build over that 30,000, you will be able to extrapolate it to the entire population of West Bengal, that is 3 crore. And based on what you learn out of this sample, and this sample must be an indicative sample of the population, there are ways in which you do this sampling effectively. But inferential statistics gives you very proper ways of doing sampling. But as long as you're able to do this, the major benefit that gives us is that it saves a lot of time and effort in terms of tabulating data, large amounts of data, and then getting to have to know what that data could indicate for us. Instead, we are able to only collect a much smaller sized data set, but a data set that is indicative of the larger population. And then we study that smaller data set and we are able to infer for a larger crowd. So it seems like a hack, but that's what inferential statistics does for us. It basically allows us to tabulate only for a much smaller fraction and then use that to basically use that smaller and analyze that smaller fraction to basically learn something about the larger data set in general. Does that idea make sense? The difference between inferential and descriptive, the kind of scenarios where you use both of these. A prompt on the comments would help me, super, great. All right, so that's the idea of descriptive and inferential statistics. Inferential statistics definitely sounds much more cooler. Sounds like the way sounds like something that helps us save on a lot of effort and time, and in the same process we are able to achieve such amazing magnificent goals. We are able to analyze a 3 crore population by only looking at 30,000 people. But then that is also the reason why this is not a easy job. It's definitely a tough job, which is why you can see that almost every year, every time an election happens, there's so many exit polls that are conducted, and most of them go heads wrong. They're way wrong. The reason why that happens is because this job requires acute statistical skills, at least the process of sampling, being able to collect the right 30,000 people to be good indicators of the population. There are several popular ways in which this sampling is also done. So when it comes to this sampling, there are major ways. So you've got things like stratified sampling. You've got things like cluster sampling. You've got systematic. There's several other random and non-random convenience sampling. There's several other random as well as non-random sampling techniques. We'll not get into the details of sampling, but sampling in itself is a science inside inferential statistics that helps you collect in an efficient and intelligent way the right target segment to basically analyze a larger group. So that is how sampling and inferential statistics contribute significantly into the learning process when it comes to data science problems. Now, in this process of discussing about descriptive and inferential statistics, we talked about several situations that happen in the industry wherein you can collect historical information, learn from that information to basically make or improve processes in the long run. And that's what data science does in a very effective way. So we talked about inferential statistics a little bit. Now, there are some popular ideas in descriptive statistics. We'll get a sense of a few of those ideas. So in terms of descriptive statistics, so descriptive statistics mostly helps us understand data. So generally, if you think about a data science or any data science project life cycle, the first stage starts off with descriptive statistics. So this is a stage which is completely meant to understand the data. In fact, if you look at actual projects in this industry, at least in the service sector, I can give you a sense. I've been in that space for a long time. If you look at actual projects, so if a project runs over a period of 6 months, it's typically this stage which is exploring the data. So data exploration that typically takes 80% of that time. It's only in the last 20% that you're typically doing modeling, you're doing transformations, feature engineering, modeling, interpretation of results, and all of that to ultimately build the processes that you're hoping to create. But the first phase of the project is the longest one, which is simply trying to understand, decipher what the data means and trying to analyze it in different ways. Descriptive statistics gives us some very popular or useful tools to do that. The first is obviously in the form of a lot of visualizations. So descriptive statistics helps us look at all kinds of visualizations, writing starting from bar charts, line plots. You got histograms, you got box plots. The purpose of these visualizations is to help you understand data better. So let's say you've surveyed a group of people for a certain use case. You're a drug manufacturer that produces drugs in the for people in the age group of 25 to 50. Now, if you're doing a survey to try and understand, let's say you're trying to make, you're probably a manufacturer of generic medicine, and you're trying to understand people's preferences or what they prefer in different kinds of situations. And you're trying to do a survey just by looking at certain visualizations for the data that you've collected. Let's say age is one of the columns that you've collected data for. Just looking at one visualization of the age column, either a bar chart or a histogram, is going to give you a good sense of how the data is distributed. So what percentage of your data can you find in the relevant age group? So obviously, a lot of companies, they do not conduct surveys and collect data themselves. This is something that is generally loaned out to companies that specialize in surveys and all of that. So you push a set of requirements to them, and let's say you've done surveys for different kinds of products. It needs to align with the kind of product that you're selling. The age groups and all of that should match, and in that case visualizations are one of the best ways of looking at univariate data points. So you've got one variable, you've got to analyze how that variable moves. Descriptive statistics gives you some of the best ways of doing it. Then you've got central tendency measures. So the broader idea would be summarizing. So summary stats. Now, summary stats again. So summarizing facts is again a very good way of describing data. So let's say you are a headmaster of a school. You just walk into a class, and there's a class of 60 kids, and you've got to understand as a headmaster how the class is doing across a few subjects. How do you find that information out? What is it that you would want to know as a headmaster? What information do you get? Should you want that gives you a sense of how well the class is doing? The 60 students in a class. You can put your responses in the comments. I'll give you a couple of minutes. You are a headmaster for a school. You want to understand how your 7th graders are doing with respect to a certain subject. What information do you need for that? What information would you want? What is the easiest way of analyzing how the class is doing with respect to a certain subject? And they've given a lot of exams, and also you have data. So what would you ultimately want to look at? You can push your ideas on the comments. Average, right? So that's one of the common responses that you would get in your head. So one of the easiest ways that our mind allows us to think about a certain idea. If I've got to look at a group of kids and I want to install a weighing machine in the school, and I have several kids, if I have to get a sense of what the weight specification should be, I can easily get some average or summary statistics, look at the data, and summary statistics would give us some of the best ways of understanding or analyzing it. Now, there are different kinds of summary stats that can be created. One of those summary stats is taking an average. So instead of looking at 60 marks, 60 different marks that each of the 60 students have scored in that subject, if you just got an average marks for that class, that would give you a sense of how that class would behave. But then there's a catch to that actually. There are two ways in which we realize or we understand summary statistics. We've got central tendency measures, and we've got measures for dispersion. Some people call it spread. But summary statistics can be categorized into two kinds of measures. Generally, when you use both of them together, that is when they work out in the best possible way. If you use them in isolation with each other, that is when they do not work out very well. To give you an example, let's say there are two classes, and there are 7 students in each of these two classes, and you're looking at the marks that they scored in a test out of 20. 7 students gave a test where they got marks out of 20. You're looking at the marks of the two classes. All right, you've got two classes in front of you, and you've got scores of every student in both these classes. You have to compare these classes. How would you compare? What do you think? Are these classes similar? Are these classes different? What do you think? And I'd like more of you to participate. So you can keep putting your inputs in your chat boxes. these classes would seem different, right? These classes seem different for the simple reason that, this class A seems like a mixture of opposites. There are some students who are very strong, these would be those students. There are some students who are quite weak. These would be these students. This student is somewhere in the average level, but there are 3 students who are much better than him. There are 3 students who are much poorer than him. If you look at this class, that's not the case here. You got 10 is obviously again seems like a middle value. But if you look at the scores around 10, even then all these people have basically scored values which are very similar to each other. So if I were to compare these two classes, I would say that class B is very much homogeneous, wherein students are mostly similar in their abilities with respect to this subject. Whereas if I think about class A is sort of a heterogeneous group, where there are some very sharp people, there's some people who are weak, and then there's intermediate people as well. So looking at these two classes, common sense would tell us that these classes are definitely way different from each other. They're definitely not similar classrooms. At least the environment wouldn't be similar, because there's some, one of them seems to be a group of a bunch of people who are strong, bunch of people who are weak. The other is very much homogeneous. But if you look at what statistics does with it, now statistics will give you some ways of analyzing this class. One of the popular ways, like one of you suggested, was average. Now, average is central tendency measure. It is a measure that helps us understand central behavior. How does a distribution or a group of data, how does a group behave on an average or centrally? If there are 50 people, and if I want one number to understand those 50 people, what number do I choose? If I choose 20, that would mean that all 50 or more are more or less like 20. That is the meaning of central tendency. Now, if you compute the average across these two classes, what are the averages? If you can give me the average for class A and class B. What is the average marks of students in class A, and what's the average marks of students in class B? Okay, class A people are saying is 10. What about class B? Same for B. Exactly. So if you look at the mean or average, whatever you call it, it could also be called a mean. It could also be called an average. If you look at the mean for class B, that also actually happens to be a 10. Now, that creates a confusion, right? Now, we just said that, descriptive statistics would give us some measures that helps us understand data better. But here it's actually creating a problem. It's basically causing misinformation. Right now, it does not seem like class A and class B are similar in behavior. Yet, if we look at a descriptive statistics measure, a descriptive stat measure, which is a central tendency measure to be precise, average or mean, we are seeing that mean for both these classes are actually one and the same, which then tells us that there's a possibility that these measures that we're looking at, these aren't always the best measures, or these measures might not always be foolproof. There might be something that we might have to do in order to make these measures effective. Now, in our case, class A or class B, both of them are basically showing us that both of them are similar. But that's not really the case. We ideally would want to be able to differentiate between these classes, because these classes are very much different. Now, the reason why this has happened is because central tendency is not something that you use in a standalone way. It's not a very good absolute measure. Central tendency helps you understand the distribution, but not always in the best possible way. Because if you look at it, 10 is a good measure for class B. The reason why I say that is because if I say that the class B behaves like a 10, I'm more or less confident about that statement, because I know that the furthest away from 10 that people go is 7 or 13, which is 3 units away. So I know that mostly people are around 10, and therefore using 10 as a central tendency measure or as a measure of central behavior seems like a good step. But the same cannot be said for class A. For class A, 10 is actually hardly what the class represents. There are groups of people in class A which are way worse than 10. There are groups of people in class A which are way better than 10. Therefore, 10 is one of the worst numbers to basically describe class A. But yet, the center tendency measures indicates that it's a 10. Therefore, what we need to realize is that central tendency must be coupled with dispersion measures. Now, what are some of the popular measures in this space? So we've got center tendency, we've got dispersion. What are the popular measures? Now, for central tendency, the popular measures are either mean, median, or mode. Whereas for dispersion, the popular measures would be range. You've got things like IQR. You've got standard deviation. So things like mean absolute deviation, MAD. So these would be some of the popular measures in case of central tendency and dispersion. We looked at one measure for central tendency. Median, also I'm sure a lot of you might be aware of. Median happens to be the middle point in a data set. If you've got a set of numbers, I simply need to arrange them in an alphabetic sequence, not an alphabet, in ascending sequence or a descending sequence. The number that comes in the middle, if there are 7 numbers, like in this case, the number that comes in the middle would be the 4th value. Because if you look at this number, there are 3 numbers to the left, 3 numbers to the right. Obviously, you'll have to write it in a sequence. If I've got these scores, I'll write like this: 1, 2, 3, 10, 17, 18, and 19. So we clearly see that there are 7 values. This value is a value before which there are 3 numbers, after which there are 3 numbers, which is why this becomes the median value. So the median value happens to be the middle point. So if you arrange data sequentially in an ascending order, the middle point of the data is called the median. That again serves as a center tendency measure in some cases. But the problem here that we identified was, if you look at the median as well, that also comes out at 10. For both classes, the median is also 10. You can check that out later. But if you look at this group, it's already arranged in ascending way: 1, 2, 3, 10, 17, 18, 19. So this is the median. Even in this case, 7, 8, 9, 10, 11, 12, 13, again, this becomes the median. So for both of these classes, even the median measure indicates that they are similar. But like we've already seen, these classes are very much different from each other, the behavior at least, which means that we need to couple the idea of center tendency with the idea of dispersion. How do we do that? We figure out some way of calculating dispersion. Now, there's several good ways. Let's talk about a few of them. We'll talk about the first one, which is range. Now, range is a simple measure. It is calculated as max minus min. So you find the maximum value in a distribution in a group. You find the minimum value in a group. You take a max and a min. So if you look at the 2 classes that we'd written, one of the classes looked like this: 1, 2, 3, 10, 17, 18, and 19. Then you had 7, 8, 9, 10, 11, 12, and 13. So these were my 2 groups. If I have to calculate the ranges for the 2 groups, can we calculate it? We've seen that the mean and median for both these groups is 10. If I have to calculate the range for these 2 groups, so range for group A or class A and class B. Range for class A should be what? 19 minus 1, that is 18. Range for class B should be 13 minus 7, that is 6. It's a simple idea. It's maximum value minus the minimum value. It is trying to capture the range of values within which the distribution is spread out. The larger the range, the more spread out the class would be. And that is what we are able to identify with this. we're able to see that, class A has a range of 18, which is 3 times the range that we have for class B. And therefore, we're able to know at the first stage, this is the first point where we're able to create a measure that helps us sort of differentiate between class A and class B based on one simple fact, that is that of range. So it's the first measure of dispersion. On mean and median, on central tendency measures, both these classes came out to be similar. But when we started looking at a measure for dispersion, that is when we start to realize the difference. So when you couple the ideas of central tendency and the idea of dispersion, that is what gives you some of the most efficient measures for describing data. So that's the idea that I wanted to drive here. The purpose was to understand that, sometimes descriptive statistics, if not used properly, can lead you to misleading inferences. When you've got to be careful with what you're using, you need to understand what is it that a certain measure or index indicates. So in this case, we saw that a central tendency measure like a mean or median cannot be used without having any cognizance of what the nature of the distribution is. In our case, we saw that central tendency measures can sometimes be good. Like for class B, 10 was a good central tendency measure, but the same thing for class A wasn't really a good measure. For class A, people were very different from 10. So therefore, using 10 as a central tendency measure for class A was not a good idea. So you've got to be careful when you're using central tendency measures. Usually when you use it with the idea of dispersion together, that is when the meaning comes out much better. And that is when the idea remains usable. Now, there are different other ways of calculating dispersion as well. There's something called standard deviation that is quite popular. What we can do is we can calculate the standard deviation for one of the classes. Let's say we look at class B. So you've got 7, 8, 9, 10, 11, 12, and 13. So the first step, let's say this is stored as X. This column is called X. So the first thing is to look at the mean value of this column. So you get a central tendency estimate. The mean value we know is 10. The column has a mean of 10. The first thing is to get the central tendency number. Then you calculate the deviation from central tendency, xi minus x bar. So this is each of the observations that you had for marks. So you're basically calculating the difference of the marks from the average marks across the class. So it's basically adding on to the idea of central tendency. If you're using mean as a central tendency measure, standard deviation adds on to it, saying that you're basically trying to compute the average deviation from the central tendency value. It's not enough to know what the central tendency number is. You must also know how every point in a group is different from the central tendency value on an average. Not exactly for every point, but on an average, how different they are. To get a sense of that, we first compute distance. Distance is distance or deviation from central tendency. 7 minus 10 is minus 3. This is minus 2. This is minus 1. This is 0, 1, 2, and 3. Now this gives me what? So this term is basically giving me deviation from central tendency, which is mean here. So you're basically computing the deviation of every point in a group or distance of every point in a group from the central tendency value. If I take an average of this, I should get a sense of average deviation. If I take an average of this, what is the average that I get? Can you calculate it quickly? What's the average of these set of values? Zero. Exactly. If I take an average of this, that gives me 0. But does that mean that on an average, every point in this distribution is same as 10 or not away from 10 at all? There's 0 units away from 10. That it does not mean that, because we can clearly see that this value is 3 units away from 10, 2 units, 1 unit, 1, 2, 3. So there are several units that are away from 10. It's not like every unit is a 10. If every value was a 10, then you could have expected this deviation to be 0. But here the average deviation comes out as 0 because minus 3 and 3 are being treated differently. When you add them up, it becomes 0. But we know that 7 is just as different from 10 as 13 is. 7 is 3 units to the left, 13 is 3 units to the right. But effectively, when it comes to talking about distance from mean or distance from central tendency, they are both equidistant from central tendency. But when they get represented here, they get represented as a minus 3 and a plus 3. which add up to 0. Therefore, taking an average of this quantity does not work out. In order to solve this plus minus problem, what we figured out, or what statisticians figured out, was to take a square of this. Take a square of this quantity. What that does is minus 3 becomes 9, this becomes 4, this becomes 1, and this becomes 1, 4, and 9 again. When you perform this step, what happens is now 13 and 7 behave like the same unit, and they should, because they're equally away, just that the deviation has been squared in this case. It's not the actual deviation. The deviation has been squared in this case. You then take an average of this quantity. When you take an average of this quantity, that is what we call variance. If I take an average of all of these quantities, what is that? 13, 14, 28 by 7. That makes it 4. So the variance of this distribution turns out to be 4. This term that you calculate is called variance. What is variance? Variance is average of this quantity, xi minus x bar whole square. So you're basically computing the distance from the central tendency measure, squaring that distance, and then taking up average of all of these distances. When you're able to do this, that is what helps us calculate the variance measure. So this term is called variance. If you take an under root of variance, that is what gives you standard deviation. So if you look at standard deviation, the standard deviation for this case comes out at 2. So you get a sense that when I say 2 is the standard deviation for this distribution, what that means is you've got to use that with the idea of central tendency. Central tendency was 10. Standard deviation is 2, means that if you randomly pick anyone from the group, he would ideally behave like a 10 or somewhere 2 units on either side of 10. So the average deviation from central tendency for any value in the group is 2 units. So on an average, if you pick any value, it's going to be 2 units on either side of 10. That is what you understand with a central tendency measure and a dispersion measure put together. So when you bring in these two ideas, when you club these two ideas together, that is when we are able to say that central tendency and dispersion together combine to give you a very decent spread and understanding of the data. So you look at any variable and you know the central tendency value and the dispersion value. It gives you a good sense of how that distribution is. You could calculate the same quantity for group B, group A as well, sorry. Can somebody calculate the variance for group A and tell me? We just calculated the variance for group B. Can somebody calculate the variance for group A? We got one answer. Let's get a few other people also to push in their responses. Okay, so a lot of answers around 55.42. Most likely that's the right response. Let's quickly do it. We had 1, 2, 3, 10, 17, 18, and 19. So the first step is to basically, this is your xi. First step is to calculate x bar. What's the average value? The average value is 10 across the bar. You then calculate xi minus x bar. So the difference between the central value and the actual value, that gives you -9, -8, -7, 0, 7, and 9. You then take a square of this quantity, xi minus x bar whole square. That gives you 81, 64, 49, 0, 49, 64, and 81. So what does this make? 49, 81 is 130. So 194. 194 into 2 is 388. 388 by 7. 388 by 7 is 5. Yes, so 55.56. No, sorry. Yeah, so 55.42 is a good value. So this is the variance of distribution B. Variance of class A. So the variance of class A comes out at 55.42. Even if we calculate a standard deviation, that standard deviation will be somewhere between 7 and 8. So somewhere between 7 and 8, you get a standard deviation. As compared to that, with the previous case, we got a standard deviation of 2. You got a variance of 4 that has now increased to this level, which means that definitely using any of the measures of dispersion, we'll be able to figure out that class A is definitely very different from class B. Although if we were trying to use incomplete learning and we just use the central tendency measure, by looking at the two classes, you would think that the two classes are similar, which means that as long as we're using the two ideas in a connected way, we are able to effectively use both of these principles to get a sense of how a data is structured. So that's a little bit about descriptive statistics. We'll now talk about how the idea of probability merges into data science, and why is it that we need the concept of probability to be around when we're doing data science problems. Now, probability is basically a math that helps us calculate the likelihood or chance of occurrence. So basically, probability basically looks at any event, looks at any process that is happening, and tries to compute what's the probability of a certain event happening. So no matter what the process is, so let's say, if you think about a bank, there's several credit card applications. For them, whether a person gets a credit card or does not get a credit card is an event. The event has two possible responses. The person gets a credit card, or the application is rejected. Now, if you've got to look at a couple of applications every day, or maybe 10 applications or 100 applications every day, this is something that can be done manually. It is something that can be scaled. But the moment you look at very large banks where there are consistent applications for credit cards or loans, any kind of lending that happens, and there are a lot of applications, analyzing it manually can become a very tedious process, which is why there are models that are built that help you analyze this. What the model does is it basically looks at any observation. So let's say a new person comes in, Ramesh comes in. It will look at a few factors. It will look at the age, probably look at the income, it will look at the savings, probably look at assets or capital. It look at several factors for Ramesh before deciding, yes, he gets a loan, no, or he does not get the card. Yes, he gets a card, no, he does not get a card. So therefore, the bank is interested in finding out the probability that that Ramesh actually is a person, and and how do you decide whether to give a card to somebody or not? The bank basically just tries to figure out whether the person needs that card or not. If you need a card, then you won't get it. If you don't need a card, you get it. That's the principle on which banks work. So if if you don't have the ability to pay, credit cards are a luxury that only people who have the ability to pay can enjoy. If the bank assesses, it has several ways of assessing it. It's got credit scores, it's got credit ratings, and a lot of that. Plus, it is able to get your complete lending history that is linked to your PAN card, and based on that, it is able to take a decision based on your previous patterns, payment patterns for anything that you've borrowed. Helps them set a benchmark for the type of creditor that you are. If you are somebody who can be trusted, somebody who makes his payments on time, somebody that ensures to the bank that this loan or this investment that you're making is not going to become a bad loan or bad investment, as long as you're able to convince the bank, or the bank is able to make sure that there's a very low probability for this person to ever default with us, they are happy to give you a loan or a card, whatever that is. Which means that probability is an idea which is of extreme importance, huge importance when it comes to data science problems. A lot of problems in data science are basically decisions. A lot of places where data science gets used are situations when you've got to take a decision like whether this person has cancer or he does not have cancer, whether this a person can be given a credit card or he should not be given a credit card. Across different spaces, whether I should spend more money in a particular channel or should I not spend more money in that channel. There's several questions around businesses that are discrete in nature, where you need a discrete response, a yes or no response. Whenever you encounter situations like that, that is where probability comes into play a part. If you want to give somebody a card, you're trying to understand whether that person is going to be able to pay back the amount that he borrows from us or not. If the probability of him being able to pay up is good, then you're happy to give him a card, which means that whenever there is a decision to be made, most likely in the background, what you're doing is you're trying to compute the probability of a certain element that you care about, certain thing that is going to get impacted that you care about. And that is how the idea of probability integrates into data science. Now, when it comes to probability theoretically, obviously you're not getting into modeling and all of that, all of those applications. But if you think about probability in general, there are three popular ways in which probability is calculated. There's a classical way. It's called classical probability. Then you've got an empirical approach. And then you've got subjective probability. So these are three ways in which people perceive the idea of probability. The standard idea of probability, we've already sort of gotten a sense of, at least at high school level, you must have come across probability at some stage. When you try and calculate the likelihood of a certain event, every time that you watch a cricket match or a football match, you would have seen that there are odds that are published before matches. Those are basically simply, probability numbers telling you what do people think, what's the people's opinion in terms of the probability of success or failure. Which means that probability is one of those ideas and which is quite commonly understood by a lot of folks. And there are three popular ways in which we deal with probability. One of them is classical. See, classical probability is probability that is calculated based on fundamental logic or reasoning. So any style of calculating probability that is based on fundamental logics, fundamental reasoning to be precise, or logic, any of those kinds of probabilities are basically called classical probability. Whenever we calculate probability based on the idea of fundamental reasoning or logic, we say that probability is called classical probability. To give you an example, the simplest probability question that can be asked is, what is the probability of getting a heads if you toss a coin? What's that probability? I'm sure everybody knows. What's the probability of getting a heads if you toss a coin? I'm not talking about the coin in Sholay. Think of a fair coin. So if you've got a fair coin in your hand, what's the probability of getting a heads if you toss it? Half. Everybody knows that, right? Everybody is comfortable with that that bit of knowledge in probability. Everybody knows that probability of a heads is half, probability of a tails is half. Because it's a fair coin, there's an equal chance of you getting a heads on top or you getting a tails on top. The reason why we are able to say this is because of classical probability. We've basically employed fundamental reasoning and logic to decide that because it's a fair scenario, because it's a fair coin, there's an equal probability of either of the two sides turning up. Unless I weighted the coin in some way, or it's the coin that was used by Amitabh Bachchan in Sholay, there's no chance that you get any different probability from the one that we've just stated. Now, this way of calculating probability is called classical probability. The other way is empirical. When you say that you've got to find out the probability for something, you basically have multiple occurrences of the event. And you find the percentage of favorable outcomes there. So basically, empirical probability comes with a formula. Empirical probability tells us, it says number of favorable outcomes divided by total number of outcomes. What is an outcome? Outcome is a result from an experiment. Any experiment, let's say you toss a coin, it's an experiment. The outcome is what you get at the end of it. You either get a heads or you get a tails. So an empirical probability is calculated in a fashion where you say what's the total possibility of outcomes and what are the possibilities which give you a favorable outcome. To give you a sense of what empirical probability is like, let's say I say that I'm going to roll a dice. I'll roll a dice and I want to find out what's the probability of getting an even face on top. Can somebody tell me what that probability is? So a dice has 6 faces, 1, 2, 3, 4, 5, and 6. Let's say it's a fair dice. My question is, if I roll this dice, what's the probability of getting an even face on the dice on top? What's the probability of getting the even face on top? Now we know that any of these faces could come on top. So what are the total possible outcomes? There are 6 possible outcomes. There are 6 unique outcomes that can happen. You can either get one as on top, 2, 3, 4, 5, and 6. There are 6 possible outcomes, out of which how many outcomes are favorable? How many of those outcomes can you say is going to be a even face? If you get 2, 4, or 6, it's a favorable outcome. So there are 3 favorable outcomes, correct? So if you have to calculate the probability of getting an even face on top, you use an empirical probability formula and you say that there are 3 probable outcomes out of a total possibility of 6 outcomes, which is why the probability of getting an even face on top becomes 1 by 2. Is this clear? Perfect. So the probability that you're getting 1 by 2 is the probability of picking an even face out of n number of different faces that you could have gotten from a fair die. You know that there's 6 possible outcomes, out of which 3 of those outcomes were favorable for you. In those 3 outcomes, the face on top would be an even face. So that gives me confidence that this empirical probability approach is a good way of calculating probabilities. Now let's say we've already talked about classical approach. A classical approach is where the same empirical idea cannot be applied for tossing a coin. So let's say I've got to calculate the probability of getting a heads, and in that case I decide that I'm going to toss a coin multiple times. Let's say I toss the coin 10 times, out of which I get 7 heads and 3 tails. This does not mean that the probability of getting a heads in a coin toss is 7 by 10. Empirical probability does not get used in this way. Empirical probability gets used in the way that we just quoted. In some scenarios, it will be more sensible to use the classical sense of probability, use classical probability as the way that you calculate probability for a certain event. In some cases, you will realize that empirical probability is a better way of looking at probability numbers. Either of the 2 scenarios, you'll be able to get a sense of probability using either of the 2 use cases. The third kind of probability that we can look at is subjective probability. Now, what's subjective probability? Now, subjective probability is something that is calculated based on personal bias, personal knowledge or bias. Okay, classical probability is something that is decided based on the idea of fundamental logic, some kind of fundamental reasoning or logic. So you had two faces of a coin. You knew that there was either a heads or a tails, and you had to calculate the probability of getting a face on top. If you have to calculate that probability, you do not need to toss the coin multiple times and check what are the number of times that you're getting a heads or a tails. You can simply say, and it would be sufficient, that because this is a fair coin, out of the two possibilities, the probability of getting one is obviously going to be half because it's a fair coin. There's an equal chance of the heads coming on top or the tails coming on top. If we do it 100 times, there's a good chance that the split will not be 50-50. But that does not mean that the probability of getting a heads or a tail is any different from 1/2. That's the idea of classical probability. It is based on fundamental reasoning or logic, instead of trying to use some kind of outcome, favorable outcome, that kind of a scenario, the formula we just discussed for empirical. Is that clear? Super. But subjective probability, like we said, is something that is based in personal knowledge or bias. So you introduce some kind of knowledge that you have about a certain event to help you get a sense of probability. To give you an example in this sense, to give you an example about subjective probability, think of a trader. So let's say everybody knows that people make money in the financial markets, and you make money by trying to predict. So let's say this is the stock price for a certain let's say I'm plotting this. You've got time on this axis and you've got stock price on this axis. Now let's say a product moves like this. Now at this stage, if you had to make a prediction and if you had to earn money in the market, you would have to realize that this is going to be increasing at this point. At this stage, if I have to make a market, if I have to basically make money, at this point, if I'm able to predict that it is going to increase rather than decrease, then I'll be holding my stock. If I know that at this point, if I know that my the share price is going to decrease instead of increase, I'll probably sell it at this point so that I get the most of the stock that I had. But most of financial investments involve trying to be able to predict whether the stock price is going to go up or go down. Now there are hundreds of investment analysts that are looking at the same stock. So let's say you're looking at a Tata stock. Now, if you look at, everybody has his own understanding of how the company is working, how the sales are going, what the company perception is. Should the stocks of Tata grow or should the stock of Tata go down? Everybody will have a different opinion. If you ask 10 different analysts, what's the probability of an uptick? One of them will tell you 20%. Someone will tell you 80%. Someone will say 60%. So the probability of going up or going down, if you try and calculate, every analyst that you come across is going to have a different view of how the stock is going to move, which means that these probabilities that you're calculating for upticks or downticks are not probabilities that can be calculated by either of the two ways. There are subjective reasons why you're calculating those probabilities. One person who says 20% might be aware that there's going to be a management shift that is going to reduce the productivity of the factories. The person who says 80% might know that the new management that is going to come in is much more stricter and is going to improve efficiencies of the company. There are subjective reasons why the probability of this event has changed so drastically across the different people that we've looked at. But if you asked all those analysts what's the probability of getting a heads on a coin toss, all of them would say half. So there are some situations where classical probability will be a better fit. There are some situations where empirical probability approaches would be a better fit. And then there are some other situations where a subjective probability might make most sense. Like in this case, where the whole discussion is so subjective in itself that it's very difficult to quantify who's right or who's wrong. Whether you're getting an upward movement or you're getting a downward movement, it's relatively pretty easy to figure out using a subjective probability idea. Does that make sense? Or see the idea of subjective probability has to do with personal knowledge and bias. So different people will have different understanding of how a certain event will happen. So if I asked a person sitting in, so let's say there was a recent Copa America final in football that happened between Brazil and Argentina. These are some of the most historic rivals. Now, if you picked out a person in Brazil and before the day of the event, if you asked him what's the probability of Brazil winning, people would say 60%, 80%, 90%, these values. On the same day, if you went to Argentina and you picked out the probability of Brazil winning, you would see 20%, 30%, 40%. Because of perspectives and bias, the probability of the same event, what's the event? The event is Brazil wins the Copa America final. They lost though. But the probability of the same event, when you look at it from these two different sides of people, you see that both of them have different ways in which they explain this probability or they calculate this probability. As a result of which that probability has very different values or meanings there. A much better example for that was the one that we took earlier, which was in the case of stock prices. Some people might know certain things about certain companies and how things are going internally, which will help them be able to predict what the movement of the stock price is going to be like in the next 2 or 3 quarters, based on which they can hedge, based on which they can protect themselves against any loss that could have happened. But those probabilities cannot be standard probabilities. Those probabilities are not probabilities that you see uniform across different people. These are probabilities that are calculated by incorporating new ideas and personal knowledge, as a result of which we call them subjective probabilities. Some probabilities are not standard. It's not, you cannot calculate a standard probability for a person having cancer. If you're building a model, looking at MRI scans, trying to predict cancer, you cannot build a model. The probabilities that the model calculates cannot be based on classical probability idea saying that you either have cancer or you don't. So it's a half chance. That cannot be the case. There you need to have a very subjective model. A model that is able to look at past data and based on that create an opinion and create a model that can look at certain input variables and decide whether a person has cancer or it does not. Does that make sense? All right. See, so that concludes the discussion that we planned for today. So what we'll now do is we'll open it up to Q&A for Q&A again. So if there are any questions that people would like to ask with respect to this space, with respect to some of the topics that we've discussed, obviously these are topics that have been covered at a very basic level. If to excel in this space, the purpose of this was to give you a basic, an intro, a flavor of what this space can offer for you. What are some of the kinds of problems that you deal with? The reason why we picked some of the topics that we did was to be able to talk about certain topics. We talked about a market mix problem. We talked about a retail situation where we talked about what Tata would do. So we talked about descriptive analysis there. The purpose was to give you a flavor of how this whole space of data science functions, how it helps industries improve what they're doing, and how this becomes so popular, to give you a sense of those examples. So if you've got any questions that you'd like me to answer, please feel free to ask. Or else we'll close out this conversation for today. So I'll be looking at the comments. Anybody has any questions around? So what we'll do is we'll reach out to you guys. So you already put in your credentials, your details. What we'll do is we'll reach out to you guys and we'll share a small course that we've created, which covers some more ideas in a little more detail. And we're offering this for free to college students. We'll give you access to our learning management system, so to our LMS, and we'll give you access to that course. It's a small course that helps you, so somewhere around 10 to 15 hours of content, wherein we talk about some key ideas in programming as well as statistics. So what we intended to cover through these sessions, we've done it in much more detail through that LMS course that we've created. So what we'll do is we'll give you access to that course, so you get a much more clearer sense of what this space is about. You wouldn't have to do anything about it. We already have your email IDs and everything. We'll share access with you. If you've already put in your phone numbers, we'll probably give you a call as well. But if you can just keep a check on your emails. Also, it'll be great if you can join the, follow the LinkedIn pages and the Telegram groups, because those are places where you can get notified on any of the new events that we keep conducting. But this is a free course that should be really helpful for you. It's about 16 hours of content when you'll be able to look through that, read some of the topics in programming as well as some topics in maths. That should help you get started in this space. We do offer full-fledged courses that are targeted towards college students as well. Courses in data science, which are priced quite reasonably, and we try and we create a program which is a work and learn program. So you get 6 months of internship as well as learning. That is something that is again that could again be something that you could explore. It's targeted towards people who are in their colleges, so that they can prepare for these kinds of opportunities and go for these roles right at the beginning. The later you go into your careers, making a switch becomes a little more complicated. But right now, at this stage, when most of you are currently in your colleges, it'll be one of the best times to basically explore this as one of the viable career choices. It gives you a lot of opportunities. It's quite rewarding in terms of payout and everything. So it could be something that you could explore. So feel free to reach out to us, visit our website, reach out to us through there, or you've already got emails from us. For any other help, you could feel free to reach out to us. There's also a certificate that will be provided at the end of this for people who had attended. Again, that'll happen during the coming week. But something that you should be actually looking out for is the LMS course. Manath, you'll have to basically tell me what is it about going abroad. So are you trying to go abroad for some masters or something? There's several people who basically pursue data science here and then go for masters, because to excel at that master's level, there's some basic level of knowledge that you need. Our courses are quite detailed. Plus, it gets you to a stage where you can actually excel in higher degree programs as well. Although if you look at it from a purely job getting point of view, you don't really need to get a master's to get a job. But if you're willing, but if academia interests you, you want to do a master's anyways, going to the United States for a master's in data science is definitely a good idea. But you must have a level of preparation before that. So either you do it with self-effort, or you join a program and do it in a systematic way over a certain amount of time. But having a good level of comfort with these skills would definitely help you and go a long way in your master's program. It really help you in that sense. So you should definitely look at least trying to do it yourself, if not joining a program. But you will need preparation before you go again to that master's course.